so we're starting to look toward acceleration, but I want to make sure that we have velocity totally nailed down. So we're going to start with our review of velocity. Velocity equation is delta d over delta t. What are these values right here? It's position, yeah. What it's saying is basically on the x-axis, those are the 2 points they're at. Those are their 2 positions, okay? So those are going to be our distances or our displacements. So we're going to take velocity equals distance final, which is 30.5, minus distance initial or initial position, which is 50, over time, which is 3 seconds. Okay, so plug that into your calculator. Tell me what we get. Negative 6 point what? And our units for velocity? Meters per second. It's meters per second because our distance units or our displacement units were given in meters. Our time was given in seconds. Okay, meters per second. Very good. And what's it mean with the negative? What's the negative tell us? It's moving backwards. Okay, it doesn't tell us necessarily it's slowing down. It tells us it's moving backwards. Okay? Very good. How far can a cyclist travel in a 2.5-hour trip if our average speed's 18 kilometers per hour? All right, so let's identify our variables here. 18 kilometers per hour. What variable does that tell us? Velocity, good. Velocity is 18 kilometers per hour because it's a distance unit per a time unit, okay? If our time is given in hours, which it is, do we need to do any unit conversions? No. All that's important is that our velocity, our distance, and our time units match. Okay, so we're going to set velocity equal to distance over time, or displacement, I'm sorry. And we'll set 18 equal to d over 2.5. How do we solve for d here? Multiply both sides by 2.5. So we're going to multiply 18 by 2.5, and we get how many kilometers? 45 kilometers. On to our introduction to our new graphs. On the very top, we've got a position versus time graph. On the bottom, we have a velocity versus time graph. Okay, both of these graphs are showing constant velocity. Okay, both of them are showing an example of constant velocity. We see constant velocity from a position versus time graph because we have a sloped line, a straight sloped line. Okay, and a slope of a velocity versus time graph tells us what value? What does the slope of a velocity versus time graph tell us? I'm sorry, what is the slope of a position versus time graph? That's my fault. It tells us velocity. Very good, very good. I'm sorry. Okay, so the slope of a position versus time graph tells us we're moving at constant velocity since it's a straight line. Since it's moving in the positive direction, what sign does that mean our velocity would have? Positive, right? When our slope is positive in a position versus time graph, that means our velocity must be positive. Okay, so now let's take a look at the velocity versus time graph. On the y-axis here is velocity. It happens to be in centimeters per second. On the x-axis is time. So tell me what's happening in this bottom example. Yeah, you're moving at a constant speed. Are you standing still? No. This straight line on a velocity versus time graph tells us that we are moving at a constant speed of 200 centimeters per second. Okay, so we've got the cruise control set. Okay, whereas if a position versus time graph looked like this, what would we say the motion was doing? If this was a position versus time graph, we'd say they're standing still, right? Their position is not changing. But in a velocity versus time graph, we read the velocity, okay? So we're telling at this particular time from 0.1 or from 0 seconds to 0.5 seconds on this graph, they're moving a constant speed of 200 meters per second or centimeters per second, okay? So those are what constant velocity graphs look like. Okay, this is still a velocity versus time graph, but we don't have constant velocity. Okay, so let's talk about what's happening here. Our velocity starts at 0 meters per second. From point A to B, what's happening? Yeah, you're accelerating. You're getting faster. You're increasing in speed. We're going from 0 meters per second to 20 meters per second in that two-second time frame. Okay? So we are speeding up right here. What about from B to C? What's happening? Constant speed. Okay? So this is like hitting the gas. This is like setting the cruise control. Okay? From C to D, what's happening? You are accelerating. You're getting faster. And are you getting faster in the positive direction? Yeah. Okay. What about here? Cruise control. You're staying the same speed. You're at constant speed here at 40 meters per second. So if I asked you, what's this object's velocity from 5 to 9 seconds, 5 to 8 seconds, wherever D to E is, you would tell me what? 40 meters per second. So if I ask you velocity from a velocity versus time graph, you just read that y-axis. Okay? From E to F, what's happening? They're slowing down. And from G to H, what's happening? Yep, you're speeding up. Okay? So we need to be able to understand what this motion is telling us. Okay? By looking at this graph, you should be able to talk me through exactly what's happening in this, 12-second time frame. Okay? They speed up, then they stand still. They speed up, then they stay constant. They speed up, they stay constant, all that kind of stuff. You need to be able to walk me through that graph. Okay? All right, here's a handout that goes with these two graphs so that you can see them in front of you. All right, so let's take a look at this velocity versus time graph. You guys need more? So on a velocity versus time graph, this time your slope tells you your acceleration. Okay, it tells you your acceleration. So whether you are speeding up or whether you're slowing down, that's your acceleration. Okay, so we can also tell displacement. We can tell how far something has traveled from a velocity versus time graph. Okay, and when we find displacement, we're saying over this time interval, we've traveled a total of 60 meters or whatever. We can tell that from a velocity versus time graph. And the way we do that is find the area under the graph. Okay, and we're going to find the area, write this down, from the slope to the x-axis. You always stop at the x-axis. So you're going to find the area from the slope, or from the line, to the x-axis. All right, so let's first go ahead and walk through what's happening in this motion. Okay, from 1 second to 2 seconds, what's happening? They're speeding up, right? They're going faster. From 2 to 3 seconds, what's happening? They're staying at constant speed. From 3 to 4 seconds, what's happening? They slow down to a stop, right? At 4 seconds, they come to a 0 velocity. Okay, they slow down to a stop. What happens then from 4 to 5 seconds? Yeah, they go backwards, right? They're going in the negative direction. This whole time we're slowing down. Right here, we're slowing down, and then we start speeding up in the negative direction. Okay, so even though the line doesn't change, we've got to understand that going from a positive velocity to a negative velocity means that we would go backwards. Okay, and then from 5 to 7 seconds, what's happening? We're speeding up. Okay, we're accelerating. Okay. Let's go ahead and find our displacement from 4 to 5 seconds. Okay, displacement from 4 to 5 seconds. We're going to find the area from the slope, the area from the line to the x-axis. So we're basically going to find this triangle worth of area. Okay, and the equation for the area of a triangle, length times width over 2, or 1/2 length times width, whatever. So this side of the triangle is 1. This side of the triangle is -2. All right, and it's negative because we're moving backwards. So we're going to take 1 times -2 over 2. Which gives us a displacement of -1 meter. Okay, so that means from this point where they've stopped their velocity, they've moved backward 1 meter. Okay, that negative is important when you're finding displacement. Okay, the negative is important when you find displacement. So you have to pay attention as to whether it's above or below the x-axis. Okay, let's go ahead and try another one here. Any questions on this one? So displacement from a velocity versus time graph means you find the area.
Where's the x go?
What x? Okay. Let's go ahead and try and find, let's find displacement from let's go from 0 to 4 seconds. 0 to 4 seconds. So is that any kind of shape that we know the area formula for? No. So what do you think our best bet is to do? Yeah, we're going to split it into shapes that we can manage. So we've got a triangle here. We've got a rectangle. We've got another triangle. Okay? We find each of those, add them together. Do they all happen to be on the positive side of the x-axis? Yep, that means we're moving forward that entire time. So our entire displacement would be positive. So for this first triangle, we'll take 2 seconds. 2 seconds times 2 meters. Times 2 meters over 2 because it's a triangle. So that gives us a 2 meter displacement for that first one. This rectangle here will take 1 second times 2 meters. It gives us another 2 meters. For our final triangle, we take 1 second times 2 meters over 2, which gives us 1 meter. Okay, so the totals for each of these little triangles we had to break up was 2 meters, 2 meters, and 1 meter. Okay, which means we traveled a total displacement during those 0 to 4 seconds of 5 meters. Okay, and I realize that our graph is technically in centimeters per second squared. I just realized that now. So essentially we'd be centimeters here, not meters. Okay, that's my bad. Okay, so questions there, yeah? So these are the types of questions that you're going to be being asked on quizzes and tests like that. I'm going to give you a graph. You have to first look at whether it's velocity versus time or position versus time. And you're going to have to answer questions like these. Find the acceleration, find the displacement, what's the position, all that kind of stuff. So you've got to interpret this graph. Okay, so how do we find acceleration on a velocity versus time graph? We find the slope. Slope. Remember? Slope of a velocity versus time graph equals acceleration. So we find the slope from 0 to 2 seconds. Okay, let's take a look at what this x-axis, what do each tick marks stand for on the x-axis?
2 seconds.
These are 2, not 1s. Okay, so be careful about the scale on your graph. Okay, but these tick marks on the y-axis are all 1s. Okay, so you've got to pay attention to those scales. We are in meters per second here, so hopefully I won't mess that one up. Okay, so we want to find the slope of these 2 points. This point right here would be 2, 2. This point would be 0, 0. All right, so if I want to find the slope, I'm going to find rise over run. Okay, so acceleration equals rise over run for this graph, which means I'm going to take final y over initial y, so 2 minus 0 over 2 minus 0, and I get 1 meter per second squared. Okay, that's our unit for acceleration. All right, let's find displacement from 8 to 10 seconds. The displacement the object traveled from 8 to 10 seconds. So when we find displacement from a velocity versus time graph, what's going to be the process here? Yep, we're going to find the area from the graph to the x-axis. Okay, our graph traveled at this line right here. So we're going to find the area from that graph to the x-axis. And this was 8 to 10 seconds right here. So the length of this side is 2. The length of this side is 2. So to find the area of a triangle, we take length times width divided by 2, which gives us a displacement of 2 meters. All right. Questions about displacement? All right, let's try the last one on your handout. What's the object's velocity from 16 to 18 seconds? Yeah. 16 to 18 seconds is this little flat line right here. We're going to go read what that line is on the graph. So we don't have to do any math here. Velocity from 16 to 18 seconds is negative 2 meters per second. That's it. Negative 2 meters per second. Because it's moving at constant velocity, we can tell that. Okay? What if on this graph I had asked you to find the total displacement of this motion? Total displacement. What if I asked you to do that? Which I'm going to ask you to do that right now. Oh, okay. You can do this on your own, and then we're going to come together and we're going to see if we agree. You're going to find total displacement of the graph, which means find the area from the x-axis to the slope, okay, on the whole graph, and add them together. So if we're trying to find displacement of this entire graph, we've got to split this whole section. Okay, this all is positive motion because we're going in the forward direction. When at this point, we're moving in the backwards direction. Okay, so that's negative displacement we're going to take away from that. The area of this triangle, I got it to be 2 meters. This rectangle was 12. This triangle was 2 meters. We all agree with those numbers? Okay, whereas this was -2, -4, -2. You add those all up, I got a total displacement of 8 meters in the positive direction. Yeah? All right, very good. Now, we've had a brief introduction to acceleration in our velocity versus time graphs, but now we're going to explain a little bit more in depth what acceleration means, okay? Acceleration in and of itself means a change in velocity, okay? Acceleration is the rate at which your velocity changes, all right? The rate at which your velocity changes. Your acceleration can be both positive or negative. We consider it accelerating. When we have something slowing down, we consider it decelerating. Speeding up and slowing down do not necessarily indicate the sign of acceleration. And I'm going to give you a rule of thumb here in just a second for the sign that goes with acceleration. Because the sign of acceleration, whether acceleration is positive or negative, has to do with whether it's traveling in the positive or the negative direction, and whether it's speeding up or slowing down. So it's a little bit trickier than just straight going in the positive or negative direction, okay? And there's a rule of thumb that I have for that I'm going to have you write down here, and then we're going to get through some problems that hopefully you can see that rule of thumb in place, okay? But when something is speeding up, we call it accelerating. When something's slowing down, we call it decelerating. That doesn't necessarily give you the sign, okay? The rule of thumb for the sign is this, okay? If an object is slowing down, so if an object is decelerating, if an object is slowing down, the acceleration is in the opposite direction of the motion. Okay, so if an object is slowing down, the acceleration sign is the opposite of the motion. Okay, and we're going to look through some examples that demonstrate that here using our equation for acceleration. Okay, make sure that we have this equation for acceleration down. Acceleration is the change in velocity over change in time. Remember we said acceleration is the rate at which your velocity changes. Okay, so our units for acceleration are meters per second squared. Okay, because units for velocity are meters per second. Our units for time are seconds, which gives us an acceleration unit of meters per second squared. All right, so this says during a race, a sprinter increases from 5 meters per second to 7.5 meters per second over 1.25 seconds. What's the acceleration during this period? Average acceleration and acceleration are the same thing. Okay, you don't have to worry about the difference between those two. They'll be used interchangeably. So that line that we saw over the acceleration in the equation, that line just means average. Okay, and that's the same thing that we're going to solve for all the time. Okay. So let's go ahead and start picking out our variables here. Okay. Acceleration equals change in velocity over change in time, which means final velocity minus initial velocity over time. Okay? So V sub F, that stands for final. V sub I, that stands for initial. Okay, anytime we have that subscript, it gives us a clue as to what that variable is talking about. So velocity final minus velocity initial. So let's go ahead and look through the numbers given to us in our problem and see if we can identify the variables that they identify with. Okay, so what's the 5 meters per second? Velocity initial. Yep, good. What about 7.5? Good, final velocity. And our time is 1.25 seconds. Okay, so we can go ahead and plug this in now. We're going to take 7.5 minus 5 over 1.25. which gives us an acceleration of what? Very good. Meters per second squared. 2 meters per second squared. So what this is telling us, what acceleration tells us, is that for every second, our velocity increases by 2 meters per second. Okay? So we are speeding up at a rate of 2 meters per second every single second. That's what acceleration tells us. Okay? And is our acceleration positive or negative? Positive. So this matches the rule of thumb. We are speeding up, which means our acceleration and our velocity were both in the same direction. They were both positive. Okay? So if your acceleration and your velocity units or your signs for those match, that means you're speeding up. Okay? If they don't match, that must mean that you're slowing down. Okay? Uh-huh. 5 is the initial velocity. 7.5 is the final velocity. So since, how do we tell?
Like from reading just the word problem.
Uh-huh. Because it says it increases from 5 to 7.5. So that means we're starting at 5, we're having an increase, and we're going to end at 7.5. Okay? Good. All right, let's take one more here. Marissa's car accelerates at an average acceleration of 2.6 meters per second squared. Calculate how long it takes her car to accelerate from 24.6 meters per second to 26.8 meters per second. All right, so let's pick out our variables here. What do we know that this number is? It's acceleration. Look at the units. Meters per second squared. That must be an acceleration. And it tells you her acceleration is 2.6. Okay? Velocity initial is? What's our velocity initial? 24.6. Good. And our final velocity is 26.8. Very good. Okay. So now we're going to plug in acceleration equals delta V over delta T. We know our acceleration this time, so we're going to plug in 2.6 equals 26.8 minus 24.6 over T. Okay, because we're solving for time here. It says calculate how long it takes her. So time's going to be the variable that we are solving for. And what's our shortcut if the variable we're solving for is on the bottom? We switch these two places. Okay, so we need to take 26.8 minus 24.6. And that gives us 2.2 divided by 2.6 equals T. That means I have a time value of 0.85 seconds. Okay, do we agree? Any questions with acceleration? Okay, I want to try one where we can look at the rule of thumb now. Okay, so just ignore what this question's telling us. We're going to say this time she's slowing down. Okay, so let's say that her car starts with an initial velocity of 30 meters per second. Let's say she slows to a speed of 15 meters per second in a time of 3 seconds. Okay, so what's happening is she's driving. She has a speed of 30 meters per second. She slows herself down to a speed of 15 meters per second. All right, over a time period of 3 seconds. So we don't care what this question's asking. Here's what number we're going to use. She's driving at 30 meters per second. She slows to a speed of 15 meters per second. What's her acceleration? Okay, her acceleration. First of all, is she moving in the positive or the negative direction here? She's moving in the negative direction? She's still moving in the positive direction, but she's slowing down, okay, which means our acceleration will be negative. Okay, so let's take a look at what the math says. Our acceleration, if we take final velocity minus initial velocity over time, gives us negative 5 meters per second squared. Okay? even though our acceleration is negative, we're still moving in the positive direction. All she's doing is going from fast in the positive direction to slow in the positive direction. Okay? But the acceleration is negative. So there's our rule of thumb. Our velocity values were positive. Our acceleration value was negative, which must mean that she's slowing down. Okay? Because the rule of thumb is if an object is slowing down, the velocity and the acceleration will be in opposite directions. Okay? Does that make sense? Okay. That's going to come into play when we do our graphing here in a little bit. Okay, we need to understand that velocity and acceleration are not the same thing. Velocity tells us how fast your position changes. Acceleration tells us how fast our velocity changes. Okay, velocity is the rate at which your position changes. Acceleration is the rate at which your velocity changes. We got to understand the difference between those two things. All right, so let's go ahead and try this problem at the bottom here. Car accelerates along a straight road from rest to 75 kilometers per hour in 5 seconds. What's the magnitude of the average acceleration? What do I say when I'm asking for magnitude? No, that's displacement on a velocity versus time graph. Magnitude's just the size, right? Magnitude's the number. Okay? We're still going to solve with the direction included, but if I ask for magnitude, I'm just asking for the number. I'm not asking for anything different. Okay? So let's go ahead and pick out our variables here. If we're solving for acceleration, we need to know velocity, final velocity and initial velocity, and we need to know time. All right? We have our time, and that's in 5 seconds. What about our initial velocity? 0. Good, because it says we are starting from rest. Very good. Final velocity is 75 kilometers per hour. Do we see a problem here? Yeah. What's our problem? We need it to be meters per second. Okay. Or we need our time to be hours, but I think it's simpler to go from kilometers per hour to meters per second. Okay, what's the shortcut we can use to go from kilometers per hour to meters per second? Yep. Multiply 75 by 0.2778, which gives us 20.84 meters per second. 20.84 meters per second. And here, are we speeding up or are we slowing down? Yeah, speeding up. So our units should match. Our velocity and our acceleration signs should match. I'm sorry, not units. Okay? So acceleration is going to equal 20.84 minus 0, since we started from rest, over 5 seconds. If the velocity of an object is 0, does that mean acceleration is 0? And if acceleration is 0, does that mean velocity is 0? Okay, I want you to think about those two things with someone sitting around you, and we're going to discuss them here in about 3 or 4 minutes. I want to hear what you have to say about this. So go ahead and turn over that handout I gave you for velocity versus time. We're going to take one quick step back to position versus time. Okay, so I want to take a look at position versus time graphs, and this is really rough. We're not going to look at the numbers. I want you to look conceptually at what's happening here, okay? So if I have a position versus time graph that looks like this, what am I doing? in a position versus time graph? You're standing still. Okay, position versus time graph. That line right there indicates the fact that I'm standing still. Okay, what does this line tell me on a position versus time graph? You're moving backwards at constant velocity. You're moving backwards at constant velocity because I've got a nice straight line. Nice straight line. Okay, so now these are the ones that I want you to write down. What happens if my position versus time graph looks like this? And it has a curve to it. Position versus time graphs are the only ones that can have curves. Okay? So I want you to tell me what you think might be happening in this particular example. You're accelerating. Do you think you're getting faster or getting slower? We start with a really steep slope. We have a really steep slope here, which means you have a really fast velocity. As we move, the slope gets more shallow and more shallow, which means we are doing what? Slowing down. We're slowing down in the positive direction. How do I know I'm going in the positive direction? Because overall, my graph is going upward in the positive direction. Okay, overall, my graph is moving that way, so I'm going in the positive direction. But the reason you can tell I'm accelerating is because my velocity starts out really steep, and it slowly starts getting more shallow. Okay, a steep velocity means I'm moving really quick, and a shallow velocity means I'm not. Okay, so now let's take a look at another one here. If I had a position versus time graph that looked like this, what would I be doing? Speeding up in which direction? Speeding up, but in the negative direction. Okay, because I'm moving backwards, my overall slope on my graph is moving backwards. And I start with a shallow slope. I start with not a very fast velocity, and then I get to a really steep slope, which means I have a very quick velocity. Okay, so do the curves make sense a little bit? Okay, please write this on your handout. You can only have a curve on a position versus time graph. Velocity versus time graphs have no curves. Okay, so curves are only position versus time graphs.